You know, Paul Falstad's simulator is not a realistic simulator for most people. We have yet to determine, or I have yet to determine, anyone has yet to determine whether or not it actually is realistic, because I have reason to suspect that my prior assessment of it may be wrong. It may be very realistic if we know to build our transformer cores differently than the way we do them. Namely, we don't use the current day powdered iron held together with epoxy resin, which is meant to destroy DC transfer. We use solid iron to support DC transfer between the coils, in addition to AC. And that's an added eddy currents, but that's also additional gain, which is what I guess people don't want. Now, you see the current is dropping off. The yellow line here is dropping off. It's going back to midline, and that's because I reduced or increased. I increased the inductance on the coils to 1 Henry. So that's for deceleration, but for acceleration I short out the coil, so to speak, if it were physical, by reducing it to 10 millihenries on the left-hand side, because it's 1 to 3, right? 1 to 3? I think so. Oh no, I'm not sure. I think it is 1 to 3. So it's right now it's operating at 1 Henry on the left coil and 3 Henries on the right coil. Now I have 1 microvolt on this battery to get things started, and I have to open up these 2 ground points and close this switch in the very beginning to bring the charge over to this side. So the point of this video is, this is a variation on Byron Brubaker's Tesla hairpin, in which I've got my 2 loads over here running off of these 2 capacitors. All my 4 capacitors are 1 farad, and they all have 3 ohms of equivalent series resistance. All the coils are 25 gauge wire. My 2 load coils are 4 Henries each, to signify 1/2 of approximately. Well, I have a twin AC motor in my RAV4 EV from 2002, and it's approximately, that's approximately what the Henries are on each motor, the total inductance, so 4 Henries on each. But in order to get the charge over to this side, I have to open up these switches and close this switch. And then the diodes here, this diode bridge, acts as a kind of a switching action to bring the charge over to this side to charge up these 3 capacitors. Otherwise, they won't get charged. All the charge will stay on the left-hand side of the transformer. So by engaging these diodes, the charge gets brought over here, and then I don't need this anymore, so I can ground out those 2 nodes, open up this switch, and you can see it's frozen at ATA volts. I think it's little a is for ATA. ATA, I think it's ATA, which is below femto, and femto is below pico. I believe that's the way that works. Anyway, and zeta is below ATA, and yocto is below zeta. I believe that's the way that works. I can't be sure. I can't remember. So the inductors are trying to catch up to the capacitors. So I have the capacitor here, and it's in the kilovolt range, and it's still rising. But the amps are dropping. Now, one thing I learned about this, the current leads and the voltage follows. So whatever the transformer exhibits the holding of current. Now, you don't get to see that, the holding of voltage on the capacitors. All you see is that they hold current, which of course capacitors don't do. But that's all you get to see. So I look at the capacitor to try to get an idea of what's happening on the transformer, because simulators never tell you what's going on in a transformer. I don't know why. I've yet to figure that one, find out what that's all about. So you have to find out about what's going on elsewhere surrounding the transformer. And I mean, I could put my cursor over it to see what it's doing, but I don't get to chart it. I don't get to trace it here for some reason. So I have it now decelerating, so its current is going down, and I'm going to run this for a while to see if the voltage finally turns around and starts to diminish and follow the lead that the current seems to be doing. Because I found it's very hard in his simulator to stop an over-unity process from happening. It's very hard and once it gets going. And one of the biggest problems I have, at least in this circuit, is that the transformer retains amperage no matter what I try to do to ground it out, short it out. Well, I haven't tried shorting it out. No, I've just been trying to ground it out, so maybe shorting would be better, I don't know. Anyway, I just thought I'd show this to you. It's very thought-provoking. It really got me to think weird, in a weird way. I mean, it's like, you know, and I don't expect this to work in Berkeley Spice. And I think I said in a prior video recently that Berkeley Spice is oriented electrically. It's electrically oriented, while Paul Falstad's simulator is magnetically oriented. And so the emphasis is different in the two styles of simulation. So you can't translate a circuit necessarily from one into the other and expect it to work. So this really goes back to a century ago, you know, Nathan Stubblefield, the Amon brothers. You know, it's more or less like trying to exhibit how that style of circuitry worked. But now I found a message that Byron sent me some time ago. I was looking for the link to this Tesla hairpin that I derived this from, that he has on the internet, and I found a message in which he talked about Joseph Newman's motor. When you put helium inside of a copper tube or a copper vessel, it creates eddy currents inside the copper vessel, just like if you had had an iron core in the midst of, you know, in the center of the coils of a transformer. And it's interesting because that's exactly what we're trying to get to happen in a perpetual motion holder device when the core is solid iron and it's not the present day fabrication of iron matrix compressed iron, you know, powder glued together with epoxy resin to kill eddy currents, to kill DC transfer, so that people can claim that, oh, transformers can't pass DC, when in fact they can if they're made from solid iron, you know, like cast iron. So Berkeley Spice, you have to use a different technique, and in the actual real world, you could go either way. You know, you could have more iron coupled to the core, or you could have of the transformer. Now, see, the Amon brothers did everything backwards. If they had copper tubing and copper sphere hollow on either side of that tubing and helium gas on the inside, and then they wound iron winding around it, and the iron was bare, not insulated, that it starts to make sense. And if they made use of any diodes, then it's quite possible they did not use, they would use aluminum on the anode, but it's quite possible they did not use lead on the cathode, such as was the case that was common 100 years ago. They might have used bismuth. That's what my guess is, because bismuth has similar properties to putting helium inside of a copper tube. And you're going to want your diodes to behave the same way, right? And you're going to want the cathode of the diode to face the copper tubing. Now, in this case, you know, this is not at all supposed to be similar to the Amon brothers' device. It was an exercise in Byron Brubaker's Tesla hairpin variation of the Tesla's hairpin circuit that he had done in actual real-world build. Let's see. So, but I was trying to do this in Paul Falstad simulator because it's easier, and even though I don't expect it to work in Berkeley Spice, now I know I can with understanding, I can be compassionate or merciful or whatever, you know, tolerate. I can tolerate the differences and not go poo-poo, you know, it's a bunch of waste of time to work in Paul Falstad simulator. No, it's not, because it's a different world. Once you get familiar with the world and how it relates to the real world, you know, this virtual reality world, how it relates to the real world, then what's to poo-poo? There's nothing to poo-poo once you understand it. Let's see, I guess I've over-talked. I've said too much already anyway. So I'm trying to see what will happen to the voltage. I already can see the amps are going down on the capacitor, but I want to see if it crosses the line and simply rises the other way. It may oscillate. You know, the waves are so long because of the inductance on the transformer is so high that I don't get to see things change rapidly. Well, I don't get to see the waves undulate rapidly, but I do get to slow down. Oh shit. Somebody had an accident outside. Anywho, I guess I'll stop talking now.